We're covering an extremely interesting topic today. We are talking about emerging architectures for LLM applications. And, it's been all the rage for all of us practically over the last half year or so. So it is extremely interesting to dig down into what do these architectures look like and how do we actually go about implementing them. And we have a couple of really amazing speakers with us today from TensorOps and from Superwise. So with that, please meet Gad and Gabrielle from TensorOps, and I'll explain a little bit about TensorOps in a second. And both myself, I'm Moran, and all are from Superwise, which I will also explain in a second. So just so you can understand the context of why we're all talking about LLMs and where it's meeting us in our day-to-day. So TensorOps is a boutique AI consultancy service, and they really do look at anything under the sun in regards to machine learning and how does these solutions meet businesses. So it's not only model development, but how does this implementation work in a real production environment for a business? And they do specialize in LLMs, time series forecast, search, and they have a lot of interesting customers here. We're on the other end of the prism here. So we're seeing LLMs as they are being deployed into production. And now there are very interesting conversations going on and very interesting needs that are arising in terms of how do we actually go about understanding what they're doing? How do we monitor them and so forth? And a lot of these conversations really do come back into the architectural level. So that is why we are doing this session today. And with that, I am going to hand this over to Gad, who is going to take you through the agenda and kick us off.
Nice, thanks, Moran. So today's lecture has a quite a special name. It's called Emerging Architectures of LLM Applications. It's not an original name. It's actually the title of a blog post by A16Z, which is an amazing read that I definitely suggest that you go and read if you haven't. However, we're just not gonna copy what they did and speak out the blog post. We have our own way of thinking of several of the concepts they introduced, and we would like to deep dive into some of them and also include some of the use cases that we see with companies that we work with. So it was just really important for me to give them the credit for the name and for the excellent work that they did there. So just saying that. Okay, so why even talk about architectures of LLMs? So maybe like a few weeks ago, there was like a lot of news about how machine learning or AI is going to take over the world and replace everybody's jobs because LLMs are so capable and they're just about to be able to do everything or anything or whatever you want. And it so turns out that actually when companies are trying to get them into production, they see that they have a lot of limitations. And often when you talk about limitations of LLMs or architectures of LLMs, the architecture is designed in order to work around these limitations in order to get LLMs into productions. And I'm not talking specifically about neural network architectures. I'm talking about the architecture of the system and the software that hosts the LLM as part of a global solution. Some of the limitations that you can see here, and I'm not going to go into each and every one of them right now because we have a whole deck of slides just to be talking about all of these. But these are some of the things and limitations that we see, and we're going to address in this presentation. I think that Moran, at this point, you have a poll for the group, right, for the audience. So we're going to kick off a poll, and we would like your opinion or your insights about what are the use cases that you're investigating with LLMs. So what kind of applications are you trying to implement? See here, machine learning augmentation, productivity generation, conversational, accessing knowledge, maybe something else. I'm gonna let people a few minutes to answer. Nice. I think if you got enough answers, maybe you can already see what are the answers. Okay, interesting. So 63% knowledge accessibility. Oh, this is great. This is just building up for the next one. So first of all, I do see a lot of duplications because, yeah, LLMs are useful for many applications, but clearly the one that takes the first place, and this was kind of my guess, was about knowledge accessibility, and that connects us really well to the first presentation, to the first topic or the first architecture that we're going to talk about, and we're actually going to talk about it quite a lot. It's kind of a design pattern that is called retrieval augmented generation. So what is retrieval augmented generation? It's a very good common use case. Most of you implemented it. I don't know if you knew that this is the name. The idea is like that, just to give you a little bit of intuition. So if I am going to ChatGPT, pure ChatGPT, and I'm asking a question about Elon Musk, then most probably ChatGPT would know how to answer questions about Elon Musk, right? What was his history? Where is he born? So it turns out that if I ask some questions about Gabriel Gonçalves, which is the lovely gentleman that's here with me from TensorOps, ChatGPT is not going to be able to know that.
Yet.
Yet, because Gabriel is like, you'll see, he's a promising persona. Reason for that, probably because ChatGPT was not trained on enough data to have it encoded into its weights, right? So there is not enough data that was put into ChatGPT within the process of training or fine-tuning of ChatGPT in order to actually answer questions about Gabriel. In a previous set of webinars, we talked about how to fine-tune your LLMs or how to train your own LLMs to train or not to train. And there is a whole set of discussion that we can talk about how to train your LLMs to include more data. So it turns out it's not just such an easy process. And there is always going to be stuff that LLMs don't know. And very often when they don't know, they tend to try to fill this lack of knowledge gaps by making assumptions. These assumptions got the name of hallucinations. And when you're talking about building LLM applications, very often these hallucinations is the thing you're going to be mostly worried about. So can we still ask LLM questions even though they were not fed initially with the information? And the answer is yes. There is this kind of technique that basically within the prompt, we're going to provide some contextual information about Gabriel. So maybe something within the prompt, like Gabriel is an AI researcher working for TensorOps, and now ask the question, or provide Gabriel's CV in some way as a text as part of the prompt, or maybe associate with a plugin to his Twitter and then get the LLM some reference data. And then we're not using the data that's already encoded into the weights of the LLM, but we're actually kind of using the intelligence or the general intelligence, not saying AGI, but the kind of general intelligence that LLMs have in order to combine these sources of information. And this, it turns out that this kind of way of doing stuff is a well-known design pattern in LLMs. It's called Retrieval Augmented Generation, or RAG. And there is quite a common architecture for that. The idea is you're getting a query, and I put in parentheses here the word user because not necessarily it's going to come from a user. And then the query is going to be redirected into the retrieval system as well as the LLM system. And then the LLM system is going to combine the information that's coming from the retrieval system to generate the results. And the results can be like any sort of generated text, like summarization or expansion or question answering or whatever application that you need. This kind of turns the whole problem of LLM into virtually a search problem or information retrieval problem. And we're going to talk about architectural considerations, but it's important to keep in mind that this is actually what we're doing. Very often you will see in these cases that the retrieval system that I just gave it like a really broad name is a vector database. So you see LLMs not just part of the LLM system, but you can also maybe see them as an embedding model. But essentially, we're talking about some kind of a retrieval system that operates together with LLMs. And you see that in use cases of code and technical documentation and library documentation and summarization and many other applications. In that point, I would give the opportunity to speak to Gabriel, as he will deep dive into how these things are implemented, and he's going to share a lot of cool tricks regarding RAG systems.
So first of all, I kind of wanted to go over the overall how these systems look and kind of point out that the LLMs in these systems are just this little white box here, right? And this kind of draws a parallel around how the early machine learning developers would be surprised at how little model code there was in their systems and how much orchestration and the things around and pre-processing would be, right? And if we look at these systems, we're so early into the LLM development cycle, and we have a lot of systems for data ingestion. We have a lot of systems for caching, logging, and things like this. And in this presentation, we'll be mostly focusing on how to get the context of these LLMs and the orchestration of different models. So I want to give you a bit of context about the limitations that we were talking about that we're going to basically use these systems to overcome these limitations, right? So first of all, these models have a very limited context window. So GPT-4, for example, has a hard limit of around 8,000 tokens. And there were some fine-tuned versions of these models that popped up later. But these fine-tuned versions, and as you can see here on the right from a research from Stanford, even though they can support these context windows, doesn't mean that the performance necessarily keeps up. And we see in this case that they were performing some document classification tasks. And the more documents they would ask to classify in the same prompt, the worse the accuracy would be. And we see that even though there are very big models like Cloud One in terms of tokens, the scaling still applies to these models. And this kind of leads us to want to be efficient in our retrieval of context to not go into this downward spiral of performance. Another thing worth considering when developing these systems is the different types of biases that can exist. So a very common benchmark for these LLMs is the LLM arena, where they kind of use strong LLMs to basically choose what's the best output between two. And what these very smart guys found out was that when choosing between A and B outputs, the LLMs would bias the first input. And this was also kind of true across all of the models that they tested. And it's a really interesting thing to keep in mind when performing, for example, what's the most relevant documents when asking an LM to choose a document. So there's also a recency bias, which is basically the other way around, which is quite interesting. When you're asking a model to perform a task, it will prioritize the task description that you gave it last, which is kind of interesting that it's the other way around. So these rack systems have a lot of these components to overcome these limitations that I was just telling you about. And they have four main steps in their development. So first of all, you want to basically ingest your data into your system. And this is done with loaders and parsers. For example, let's say you have a knowledge base in your organization of a lot of PDFs. You basically want a PDF loader that can be very good with your specific documents. For example, if your documents have a lot of tables, you need to maybe use some OCR technology to extract some meaning from these documents. Then you need to pre-process these documents in a way that you can store them. So for example, you could chunk them into smaller pieces of content that you can store and index, for example, with a vector database. And then you need to define a strategy to retrieve these documents in a way that is efficient and that works for you. And there are a lot of ways to do this. And this is kind of a point that I really wanted to get across, which is in these LLM systems, since they're all very new, we tend to focus on the trendier and newer things like vector databases and some very specific LLM focused companies, for example, like Unstructured. They do data ingestion and they're very marketed to LLMs, but no one's really stopping you from using whatever you're using for machine learning data ingestion for the last 15 years, right? So in this example, we show Airflow and Databricks, but you can really use anything that you want to use as long as it works. And the same thing really goes for vector databases. And I really wanted to focus on the vector database argument because we see that a lot of these tutorials recommend that you use a vector database without even really thinking about it. And it really feels kind of like everyone gets a vector database. It's like you get a vector database, you get a vector database. We all use vector databases for our models, right? But the thing is, there's so much search expertise these days that there are a few exceptions in the applicability of these databases. For example, let's say you're storing news about a football club, right? And you want to ask a model, what's the status of this club? Like, how's it doing lately, right? But if you have 20 years of news and you're going to do embedding similarity with this football club, you might get news that are 20 years old that are absolutely relevant to determining the current success of this club. And the same thing happens if you're asking, for example, for vulnerabilities about Windows 10. You have a bunch of documents about these vulnerabilities, and these documents might mention Windows 11, but the embedding of Windows 11 and Windows 10 are very close. So you might get some cross-referenced documents here that are going to result in very poor outcomes for LLMs that might mention vulnerabilities that don't exist, which might even look like hallucinations, but they're the retrieval system's fault. So I also wanted to kind of go over some advanced retrieval augmented generation architectures that can basically post-process your retrieved documents in a way that can really improve your accuracies. So for example, like I said in the news example, you can add a time component to your similarity search of your vector database to avoid this problem of looking into too much into the past. And then there's some interesting ways to use LLMs to post-process your retrieved documents. So there's relevance reorganization, where you basically ask another LLM, usually a smaller one just for cost concerns, to reorder the documents you retrieved in a way that puts the most important ones first. You can also do contextual compression, where you basically take your retrieved documents and you ask the second LLM to remove the irrelevant parts of these documents, resulting in a much better summarized and basically efficient context. And there's also self-querying, where you use a separate LLM to take your user query and make it into a structured query that can even interact with things like SQL databases. For example, a few months ago, Google released SQL Palm, where you can basically give it a natural language query and it will turn it into an SQL query. And if you think about it, in this case, we can even replace vector databases with an old thing like SQL by using LLMs.
Yep. So I want to jump in here. By the way, great question here on the chat. How do we overcome how basic, like essentially like a prompt is a way to query an LLM? How do we engineer the prompt to like get better and better results? I think there is like a whole philosophy that we actually plan to have a webinar on that as well, on like how to do prompt engineering successfully. Some of it is done with LLMs themselves. I wouldn't go into like all the techniques. I think that this one is an example. This one is a great example of like an advanced way to do reg systems, specifically around how to generate the correct prompts or like the efficient prompts. So I don't know if you heard of Flare, but Flare is a technique that essentially kind of understands, helps you like in an iterative process achieve better performance than out of the box RAG. The idea is like that. When the LLM is emitting a response from you, for you, it's basically can emit also the confidence that it has in each token. And sometimes it can show you that it has lower confidence in some tokens. Very often that would be associated with some conflicts within internal data that it has. So within your system, you can try to set up this manual threshold, and I cannot believe I'm saying that, like manual rule-based threshold to your system, in which you are going and asking the LLM to refine the prompt for these specific tokens that came out with lower confidence. You're going over this again and again until you're refining the prompt well enough, and until the retrieve data and the prompt together provide you with a response that generate a response that has good enough confidence in all the tokens. And that is like a really interesting technique to implement. You see here an example of like Joe Biden, where in some process of the retrieval, it ran through an LLM. It says that he went through the University of Pennsylvania, the confidence of Joe Biden went to the University of Pennsylvania happens to be low, so we run some retrieval again, and you see that no, he actually went to University of Delaware, and this is how we, through an iterative process, refine the prompts, refine the retrieved data, and also refine the eventual generated content. But it's not all about RAG systems, even though I must say RAG systems are, I think in the poll, we got like 63% of the people saying that they're doing RAG systems. From the perspective that TensorFlow sees, it's 90% of the cases. This is something that is very exciting for me, somebody who's been in machine learning since 2014. And this focuses on orchestration. And let's talk about orchestration. So if you have been around data science and big data around 2014, 2012, you probably heard of Hadoop, and Hadoop has this magical concept of MapReduce. So I'm trying to count the words, for example, in Harry Potter, and I want to understand how many times Harry and Potter appear in the document or in the book. And there is a technique. You basically separate the document or the whole book into smaller documents that you can process easily in weaker machines, and then you perform some kind of reduction. So it's a nice algorithm that works well when you want to count words. The whole strategy of deciding how to split the data to do the mapping and then how to do the combination, which is the reduction, is made is deterministic in a sense, and there is no AI involved in it. Essentially, when you're thinking about it, very often machine learning pipelines look like a MapReduce, where the result would be the input for the machine learning model, right? You would take a whole bunch of data from like raw events, and then you're aggregating it and cleaning it, and then eventually you're left with this clean set of data that goes into your machine learning model. But what happens if your task is not to like classify, TF-IDF over Harry Potter? What happens if your aggregation is more complex? You want to generate a summary of Harry Potter. Then Hadoop Harry Potter is not going to reduce. It's not going to work in this case, because the kind of strategy of like splitting it to random chunks and then aggregating back word counts it's just not going to apply. RAG is also not going to apply because there are not good enough LLMs, at least from my knowledge, that can take all Harry Potter and generate a good summarization. So what can you do when you want to generate content, or when you want to do generation using LLMs based on a massive content? So at this point, I'll give it back to Gabriel to speak of some of the solutions.
So basically, in this case, we're kind of tackling a problem that cannot possibly be tackled by a single LLM. And this is kind of the same inspiration that was there for computer programmers back in a long time ago when they were trying to develop, for example, parallel computing, right? So essentially, we want to find a way to divide this work. So we want to chunk our books or our documents in a way that can be either by characters, for example, or document relevant. For example, a book, you might want to split by chapters. And then you want to run these chunks through LLMs, and you will obtain a bunch of results for intermediate summarizations or intermediate whatever you're trying to generate. And you need to define a way to merge these intermediate results and with another LLM and get a result that makes sense and that takes into account all of the book or all of the documents equally. So this is quite interesting because it places the LLM or the AI model in a different place in the pipeline of AI systems. So you would usually pre-process things and use the AI afterwards, but now you can have AI within the MapReduce of pre-processing things, or you can even have it as a pre-processing step itself, right? So it's quite interesting how these things are changing and how dynamic this field is in this aspect. So I was talking to you about these merging algorithms, and essentially there's quite a good parallel to MapReduce here. So that's what, for example, LangChain calls it. So this strategy essentially consists on splitting by any rule that you decide to split it by, and then have a prompt that tells the model, okay, there's two results, merge them into something that makes sense and it's small enough. And then you keep doing this merger until you have a result that fits in your context window. And this final result will take into account all the chapters equally or somewhat equally. There's also the refine approach, which is a lot more sequential. So basically, you get the output for the first chunk of document, and then you get that output, you provide the second chunk of the document, and ask the model to refine the first output. So you would summarize chapter 1, then give it the summary of chapter 1 and chapter 2, and ask for a wider summary. So this is mostly done usually using LangChain, also LaMindex, although they call the MapReduce tree summarize, which is essentially the same thing. But this MapReduce pattern is certainly going to be as ubiquitous as the MapReduce pattern was in the early 2000s and became a very normal thing to have implemented in your own frameworks and systems. And nothing is really stopping you from developing these prompts by hand as well. So you can implement it in any way you see fit, really.
Okay, so now I would like to focus on the monitoring part of the architecture. So just a minute. Okay. So as you can see in the architecture, we have a dedicated place for the monitoring. And in the next few slides, I would like to drill down into it and try to understand which data is available for us and which metric we can extract on top of it, and how eventually, once we detect some issues, we can resolve them, and what are the options that the actions that we can take. So before that, I just want to different between the LLM evaluation and LLM monitoring. Once we're talking about LLM evaluation, it's basically a way for us to compare between different models, different fine-tuned technique, different prompt approaches, and eventually we will get a score that will help us to understand which is the best model for us, and then we will deploy to production. This is like a very hard task to evaluate how good an LLM is, and we can think of multiple metrics and measurements. Some of them are context aware, that we need to understand which task we are trying to evaluate, and some of them are just measuring the overall intelligence of the LLM. There is a lot of measures behind it, and we need to choose the best one for our use case. There are a lot of benchmarks in the field of language models, and I think the most common framework is Evals of the open source from OpenAI, which enable you to evaluate your LLM against multiple benchmarks in the field. So just again, to emphasize, the evaluation part is an offline. It's not part of the architecture. It's not part of the production implementation. It's something offline that's related to the offline research phase. We can choose a different model, select different prompts, fine-tune the models, and eventually, once we are satisfied with the performance of the model, then we can deploy to production. And then monitoring takes place. So when we're talking about monitoring, basically, what is the main difference between monitoring an LLM model compared to classical machine learning monitoring? So one of the key differences between them is that let's take, for example, data drift, which is one of the key measurements we are tracking on classical machine learning systems. We try to measure how much the production data is different from the training data set, because like the assumption that if the data is not looks like the training data, the model assumption, and probably the model is suboptimal. But what does it mean in the LLM area? Basically, we are not always aware of the data that the model was trained on. It could be like it not even reflected to us, or if we have it, it could be huge, and it's really hard to extract statistical measurement on top of it. So once we are going to the LLM, some of the metrics are not relevant anymore. Another big difference between the two is the path to resolution. Once we detect some issue, in classical machine learning, we probably retrain the model or add some features in the feature extraction phase and things like that. But once we are talking about LLMs, there are few other solutions that we can take. Like we can improve our prompt engineering process. We can change the retrieval process. We can fine tune the model. And having a clear observability on the entire flow will give us the ability to pinpoint and understand where the model is not performing as expected and to tackle it directly. So once we are talking about machine learning monitoring, LLM monitoring, as Gad and Gabriel showed before, the main process is like we're taking a user query, we can enrich it with some additional data from VectorDB or from other sources, and then we can take the prompt and the context and invoke the LLM, get a response, and eventually we might get even the user feedback. Each one of those surroundings for the model, we can track and monitor separately, and get them into one observability platform. And then once we will have observability on the entire pipeline, we can understand when we are not doing as expected, and we can act accordingly. So we are not monitoring the LLM itself. We are talking its surroundings, the query, the context, the response, and the user feedback. In the next few slides, I will go on each one of them and see some example of metrics that can be relevant. Okay, so the first thing that we can monitor is, as I said, the user query. We can think of a lot of metrics on top of it, like sentiment score. We can classify the query into some topics. We are getting more prompts in sports or politics. We can find prompt injection, like try to see if someone is trying to attack our LLM. We can detect some prompt types if we are using like chain of thoughts or few-shot learning and things like that. And when we go to the next phase, the retrieval process, it's a very complex engineering system and it can create a lot of bugs, and a lot of failures can be detected on top of it. So we should give it we should treat it and measure it like an information retrieval task, and not use like classical machine learning measurements for that. And basically, the core concept here is that most similar is not necessarily means the most relevant context. So for example, we should think about a way to measure if the user queries are even covered by the vector store. If we have some answer that we can answer and enrich the user prompt, we can think about ranking metrics and see if like the retrieval system is performing in terms of selecting the most relevant chunks. Maybe we are selecting chunks, but those are not relevant to the question at all. They are just similar to it. And we can even think about using another LLM and to ask them to score the relevance of the context. Each one of those measurements can take us to a different resolution path. We can expand our knowledge base. We can refine our chunking strategy. We can enriching the context understanding of the model, and so on. In the next phase, the model response, we can generate a lot of metrics on top of it as well. We can count the number of refusals. So for example, in this example, I asked ChatGPT to share with me the developer's personal details, and it gave me like a generic answer that it cannot provide personal details about developers. So we can count those generic answers and create a measurement on that. We can compare between the question and the answer and see if we are getting like drift in the similarity score. We can look for PII data and so on. And in the last phase is the user feedback, which is the most valuable for us, but it's also it's very hard to collect. Once we have user feedback, we can try and slice and dice and see patterns and trend and areas in the data that the model is underperforming. We can basically split the feedback into two types. There is the explicit feedback, like ChatGPT. Once you're getting an answer, you can vote like thumbs up or thumbs down and count it and create measurements on top of that. And there is the implicit feedback, when we are like, for example, Copilot, GitHub Copilot. If a user like accepting the suggestion of the model, it's probably mean that he is happy with the response of the model. So we can infer it out of his action. And we can even like create more feedback metrics based on another LLMs, like how well the response entered the question. We can invoke another LLM and get his feedback and measure that. So to sum things up, we talked about 4 different phases of monitoring. Each one of them has its own measurements, and it can give us a lot of information about where we are underperforming, when there are difficulties, when something is broke, and we can act accordingly. And because it's very hard to create those metrics, that's why we create in supervised LMeta, which is an open source package that creates those meta features on top of your text automatically.
So after all of this, you've probably also heard a bit about other architectures aside from RAG generation systems or RAG systems. So basically, I want to talk to you a bit about the agent architecture, because these agents, however, a bit more experimental, they can perform some really cool tasks, and they look a lot more flashy when they work. So these agents essentially consist into using the language capabilities of the models to decompose a task into smaller tasks that can be understood by the model. So this model will then execute these small tasks and decide by itself when to resort to external tools. And then it can use the results of the tools to reflect on the results and present them in a way that is refined to what the user asked. So to do this, it requires that we prompt these LLMs in very specific ways. So we kind of wanted to reproduce the way a human thinks, but in text. So the first kind of more naive approach to this problem is to simply ask the model to explain the answer step by step. And just by doing this, it's very surprising how much better the results are when performing certain tasks. But of course, this was refined and there were a lot of research papers. So the biggest thought framework that is used for this is the React framework and not the front end one. Which is basically consists into decomposing tasks into action, observation, thought, loops. So you loop around these 3 things until you get a final answer that the model is very confident is right. And built on top of this was basically the reflection framework, which essentially consists in using React framework with a component that first of all detects, so this heuristic kind of detects if we're going into loops that are infinite. And reflection basically asking the model if it's doing what it was told to do. So you get an output and then you ask the model, was this output relevant to what I asked you? Does this output conform to the norms that I asked you to do? And it will very often result in a very big improvement in accuracy, like we can see in the Alford benchmark here in the bottom right. We see that just by adding reflection on top of React, we had huge increase in accuracy, which I thought to be extremely interesting and really shows we can really break the barriers of these already reported big LLMs performances. So these agents, I said that these agents have the ability to decide which tools to use, but these tools didn't really exist before them. So I just wanted to go very briefly into what these tools are. So these tools essentially consist in just a function that accepts a string and that will run some other function. Basically, this function can be a Python interpreter that is contained within it. It can be Google searching. It could be fetching a a website using Selenium or something. So it can be really anything. And as long as you program these functions and you describe them in a very good, and like if you're very descriptive in the way you describe them to your LLM, it will know exactly when to choose them, and it will really use the results that it gives them back to provide you answer that you didn't think were possible.
Yep. So this is kind of like, thanks, Gabriel. This kind of wraps up like what we spoke about. Even though we thought like AI is going to destroy the world, LLM are super capable, it can do everything. It turns out they are limited. Every time we break some limitation, we do find out like integrating them into real production systems is a little bit complicated. These architectures are actually meant in order to help them be part of real life production systems. We saw RAG as a very famous architecture that, again, in my perspective, 90% of the things that I see is RAG. Orchestration, monitoring, and agents. We got a bunch of questions. There is already one that I would like to ask Gabriel regarding the last chapter that I think is interesting. Gabriel, what's the difference then between an agent and a plugin?
So it's usually plugins are more all-encompassing. I think that the question is more between agents and tools, but agents are usually not as integrated with a specific tool as plugins. Basically, that's kind of the broad answer.
Again, like so again, like what's the interaction between agent, tool, and a plugin? Because so if I understand correctly, there's a question here. So like a plugin is basically you allow like the LLM to get some access to an external API or to external tool. You're like growing an arm, and then the LLM can decide to use the arm. Would that like the act of deciding to use the arm, would that be the agent?
So the agent is the model that essentially decides, and it has access to all these tools. It's a bit hard to put my finger on what exactly the agent is because it's kind of a system, right?
Mm-hmm. Okay, so essentially, you'd say like the agent is like the architecture in which, or the design pattern in which the LLMs make the decisions themselves through the process, and then often these decisions are either tools or plugins, right?
Yeah, and then after you have all these things basically programmed and this whole huge ecosystem of plugins and tools, then it's really hard to say what is the agent at this point, because it's kind of all of it, because it was done for the agent, right?
Yep. Nice. I got like another question that I think that I can take about how can you speed up the inference of LLMs. So we didn't treat. So if you look at the, again, A16Z diagram about all of the components of that they mapped in LLM architectures, there is one about hosting your own LLMs. There is the question of host your own LLM versus using an API. And for each and every one of those, there are techniques to speed up the inference. So we didn't choose to speak of those, mostly because these are questions that are also applicable for traditional machine learning, and they're broadly discussed. There is a lot of consideration, like let's increase the size of the machine, let's distribute well. However, there are cases that are more specific to LLMs, right? So we do know that generating more content or generating bigger responses can take more time. So sometimes limiting the amount of tokens that we want to generate is helpful in getting quicker results. If we're talking about user experience, then streaming versus not streaming, testing out different APIs. So we do know, for example, that OpenAI had times where they were returning answers slower. So wrapping your service against like, so building an abstraction layer between you and the API and going to the API that is faster, that's also a technique that is feasible. In the previous webinar, we spoke about techniques to reduce the size of your LLM. So maybe ChatGPT is very capable. ChatGPT is like not open source, you cannot do that. But maybe Falcon is very capable, but it's too big, so it takes it a lot of time to return an answer. Maybe you can do some fine tuning to make it more specific to your use case, and in some process that is a little bit similar to distillation or model refinement, you're retraining your whole LLM to generate a smaller LLM, and then you're reducing the strain on your inference system. I would say that it's a really complex complex answer, because there is just no like one technique to do that. One thing that I really liked doing with one of our customers was caching. So when you think about caching, very often in LLMs, you kind of assume that you would have to generate the response online, because who would assume what the user is going to ask us about that information? But it sort of turns out that sometimes you can use the LLM in order to do that. So with one of our customers, while we are processing in the data, so once we're loading in incoming raw data, we ask the LLM, what are the questions that the user might ask? So let's say I'm preparing like a technical document of Windows. And I can generate an FAQ on that specific document. And then I can then cache these results like by question and answer. And when a user is going to ask me a question, I can embed a question, see if something similar was already asked, and then just provide a pre-generated response. And that, of course, can yield in some reduction of the inference time, which is a little bit cheating, because I'm not talking about specific reducing the inference time of the specific LLM, but this is life. Like this is eventually LLMs do not live in a world of their own. They live in production systems, and with their limitations, these are the things that we overcome.
Cool. So I'm going to hop in for a second to make sure we get a little bit more questions answered. We still have a few minutes left. So we have one question here, I think, that is more around safeguarding. So how can we tell the model not to give results that are out of context, non-suicidal info, basically some filters before returning the result? And can this be achieved only through prompt engineering? And if you didn't get from my opening, no, it cannot. It can also be achieved through other ways, or are there other ways to do this? So I know both Ol and Gabriel have inputs into the subject. So one of you, why don't you guys start it off? Because there's two sides to this. Gabriel, you're up first.
Sorry, I was muted. So basically, you can do this. You can kind of mitigate a few results through prompt engineering, and maybe even in the way that these models are trained. But it depends on what are the consequences of your or bad outputs, basically. So I would say my suggestion would be maybe try and think about a model that can filter out these outputs. So you can kind of fix this LLM problem with more LLMs, and you throw another LLM into problem, and you might really get a good result here. And this is what a lot of AI safety companies are doing, which are you can fine tune LLMs to be specific to this safety metric of the outputs of another LLM. And they don't necessarily need to be as big as the GPT models that we're using right now. So there's a whole other system behind validating answers in a way that are very safe.
Okay. Oh, why don't you take like the flip side of that? Because we all know that the downside of LLMs to LLMs is trying to figure out why they've achieved certain things.
So we can think of it like from another perspective. Basically, the concept of guardrails. So we can take like once the model give the response, we can add a post-processing step, which take this prompt and try to see if it's like offensive, if it's contain PII data, and things like that, and then filtering out and replace it by generic response, and then send it back to the user. This is all the concept of guardrails.
So There's a lot of additional questions here, and I think a lot of them we're going to address in the follow-up here. But there was an interesting insight looking over in the chat here, specifically looking at, does anyone feel like ChatGPT is now not as relevant as it was in the early days? And I think everyone on the panelists here today has, opened practically every open source model that's come out in our field and had a chance to play around with it and integrate it and see it in real life systems. So I think, why don't we close with, where do you guys feel we started off, where there was really this like ChatGPT boom and everything was ChatGPT, and now when we're seeing additional models come out, how is this going to change the playing field for everyone? So Gad, would you like to kick us off?
Oh yeah. My swing of emotions from regarding OpenAI goes from, I love them for what they did for humankind, like pushing forward, like releasing these models, between hating them for like data privacy concerns and like and I think also like that's like the emotion that we're getting from people. Definitely they had an edge there. They came out first with amazing models. It looks like it's something that others cannot close the gap soon enough. Nevertheless, a few months later, you're getting more and more open source models. We do know that it's not just probably it's not just the models and the technology, but it's also the amount of resources that they put underneath. So there were examples on how ChatGPT becomes less and less good over time, and nobody knows exactly why it is. Maybe it's because of some poor fine-tuning that they're doing over time, or maybe it's because of some versions that use less resources because they want to make the model more profitable, so or lose less. So I'm not sure exactly like how OpenAI stands today, and there's a bunch of benchmarks. We do see the gap is closing, and prophecy. I don't know if it is in English. In Hebrew, we say that prophecy is given to the fools. So I'm not going to make a prophecy, nor even an estimated guess. But what I can say that happened in the past, when computer vision came out, Google had like these ResNet architectures that really struck as like amazing benchmarks. And now convolutional neural networks are kind of a commodity. We also saw that in image generation, and then came stable diffusion and some other models, and like more people learn how to replicate the science. And the question is really about the whole engineering of the system, whether and also like the economy of it. Like, do you have partners to support you? Do you have contracts? Is your legal system gives your end users enough confidence that they would allow you to send, they would allow sending their data to you? So I think that these are the questions that are going to lead decision makers in companies regarding to which LLM to choose. Price, availability, quotas, privacy concerns, legal, many of these, and not necessarily the quality of the models.
That was a really great answer. Or Gabriel, do you guys have anything to add to that?
So I'm totally agree, and I might add that, as Gad said, like the mod, if we are looking about the model itself, the gap is closing. But behind this model, there is a huge engineering system that supports it, like for retraining, for serving. And I think this is like their biggest advantage in relative to like open source or other companies. They are a very mature engineering organization to support it. And that is something that will take time to close.
Awesome. So with that, we've hit time. So first of all, this is an ongoing series. So there is a series on LLM training. If you haven't caught that, you can find it on the website, and it will also be in the follow-up materials as well if you want to see what we covered in the past. And if you did not guess up until now, the next session will be all about prompt engineering, and we will focus much more on that. Please, if you have anything that you thought that we were going to cover during the session that we didn't touch on enough, or you would like to receive additional information on, please go ahead and just email us and we'll try and give you the best references. And we might end up spinning up an entire separate webinar just on your question, depending what it is. So thank you everyone for your time. We really appreciate you all taking the time to join live, and we will see you for the next one.